Hi, today I'm going to be talking about power and electric circuits. To start off, I'm going to define the electric circuit. It's an electrical network composed of individual electronic components, such as resistors and capacitors, connected by conductive wires through which an electric current can flow. Now I want to draw out a simplified version of what an electronic circuit would look like using a resistor and a conductive wire through which our current will flow in order to visually demonstrate this process. So to start off, we have this line, which represents our current. Then the zigzag line, which represents our resistors, and then it ends with our current. Now a current is the rate of flow of which an electric charge passes through a given point or region. In its unit form, a current is an ampere, or the amount of charge over a specific period of time. Now above, on our model of a circuit, we'll see these three circles here, which represent our negative charges. In a conventional current, the electrons are the ones being attracted by a positive end, which is why the electrons or the negative charges are the ones to flow through to create this current. However, there are cases in which both positive and negative charges can simultaneously flow through to create a current. However, in this case, we are going to define these as electrons. Now, as we can see in this illustration, the electrons are going to flow from the right to the left. As the charges flow, this creates a current. And as the charges flow through the resistor, this creates a voltage. We will define both of those later. Now, a resistor is defined as an electrical component that limits or regulates the flow of electrical current in an electronic circuit. A real-life example of a resistor would be something used in an LED light. For example, if there is too much current that flows through an LED light, this will cause the LED light to explode or to become destroyed because it can't handle that amount of current. A resistor in this case will limit the amount of current flowing through the LED light, which would allow it to function properly. And the unit for resistor are ohms. Now, a voltage is defined as the electrical potential difference between 2 points, or work needed per unit of charge to move a charge between 2 points, and a voltage is created when the current flows through the resistor. Now, the units for voltage are volts, which are joules over coulombs. Now, in order to further demonstrate how a current creates power in the circuit, I'm going to clean this up, remove all these definitions, and we're just going to look at the basic example of what a circuit is. Now here we have our circuit. We have our current, we have our resistor, and we have the negative charges that are flowing from right to the left through our current. And in this case, I'm going to add these negative charges to them just so we remember that these are negative charges or electrons that are flowing through. Now, like I said before, as the negative charges flow through the resistor, it creates a voltage or a change in electric potential energy. Before the charges reach the resistor, it is at a state of high electric potential energy. We're going to illustrate this by adding this arrow and demonstrating that at this point, this is our initial voltage, which is a high electric potential energy state. Now, as the charges pass through the resistor, its electric potential energy decreases and leaves us with a lower electric potential energy. We're going to represent this on the other side of the resistor with this arrow and V2, which is our final voltage, and it's in a low electric potential energy state. Now, to demonstrate this change mathematically or quantitatively, we're going to use the equation on the right, which is our voltage equals the electric potential energy per unit of charge. So the voltage is the amount of potential energy there is per charge. So based on this equation and the fact that we know that the electric potential energy decreases as it passes through the resistor, the amount of potential energy per charge is less than before. We've lost electric potential energy somewhere. So where did it go? What happened to that? Due to the law of conservation of energy, we know that energy cannot be destroyed. So that electric potential energy didn't just disappear. It had to have been converted into something. Based on other physics concepts, we may assume that some of that electric potential energy was converted into kinetic energy as it moves through the resistor. However, this is not the case, as the charges don't speed up, so there is no increase in kinetic energy. So what happened? In this case, the missing electric potential energy has been converted into thermal energy, or heat, which was taken up by the resistor. Earlier in the video, I defined a resistor as an electrical component that limits or regulates the flow of electrical current in the circuit. This is done by transferring energy from the charges into the atoms and molecules of the resistor. As the charges flow through the resistor, they hit the atoms and molecules in the resistor, transferring energy and causing them to oscillate or move more quickly. This creates thermal energy or heat, in turn heating up the resistor. That's why often resistors are hot to the touch. Now this concept is referred to as power dissipation, and we can find out how much energy the resistor is gaining per amount of time by using the formula for power. This will determine how much power there is in electric circuits. Now power is defined by the amount of energy over time, and we can see that on the right under our list of equations. The energy in this equation is the amount of energy gained by the resistor, which is also the difference in potential energy, because we went from a high electric potential energy state to a low. So the amount that we lost is going to equal the amount of energy in our resistor. So below, we can use this equation by saying that power equals the amount of energy over time, which also equals the change in electric potential energy over a specific period of time. Now on the right, we can find the equation electric potential energy equals charge times by a change in voltage. Using this equation, we can take it another step forward below by saying that power equals the amount of charge times by our change in voltage, which is V2 minus V1, over our change in time. Now to go one step further and to break down this equation even more, on the right, we can see that we have the equation I equals Q over T, which is I, our current, equals the amount of charge over a period of time. Now, seeing the equation below, which we have for power, we can simplify that charge over time right here to say that Q over T equals current, which means that power equals current over the change voltage. Now the SI unit for this is going to be joules per second, which equals watts. On the right, underneath our equations, we have one final equation, which is our change in voltage, which equals current times by resistance, and this is known as Ohm's law. Now, due to Ohm's law and the equation that we have for power, which is power equals current times by change in voltage, we can determine that there are other forms and ways to solve the equation for power and to determine how much power is in a circuit. Ohm's law allows us to substitute for the information that we may not have to determine the power. For example, if we didn't know the voltage, we could find power by saying that power equals the amount of current squared times by resistance. And if we didn't know the current, we could find power by taking the change in voltage squared and dividing that by the resistance. Using these equations, we can determine how much power is in a circuit. Now let's do a practice problem so we can determine the power in a circuit due to a resistor. Now let's say that we have a current which has 20 coulombs of charge flowing through a given area over a 2-second period of time. Now we also have a difference in potential energy of 5 volts. Using the equation, power equals charge over time times by change in voltage, which also equals current times by change in voltage, we can determine that 20 coulombs of charge divided by 2 seconds, or our current, times by a change in voltage of 5 volts, would mean that we have 50 watts of power. This is how we can determine how much power is in an electric circuit.